this video, we're going to be looking at how to find the arc length of a circle. So just like what we did in class, we were looking at finding the area sector of a circle. So the area was just a portion of the whole area of the entire circle. So we talked about doing it a couple different ways. Let's just take a minute and recap what we learned in that lesson about finding the sector area. So in here we have a do now. It says in the diagram below of circle O, diameter AB are radii with OC and OD that are drawn in there. The length of AB is 12, and the measure of angle COD is 20 degrees. So it just couldn't fit in the picture a little bit. So remember, we're talking about the angle COD. This 20 degrees is in that little nook up here. It's also telling us that our two arcs, AC and BD, are congruent. So this here, AC and BD, are congruent. Now we want to find the area of the sector of BOD. So in this case, there's a couple of things we have to keep in mind. So there's two ways we can set it up. You can either use a proportion, because remember, if you're finding a portion of the whole entire area, we can set it up using that idea. Or we can multiply our portion of the angle by the entire area to get the portion as well. So when I look at this, first off, I'm trying to find the sector BOD. So there's a couple pieces I got to make sure I don't get tricked by. First off, I need to realize that my diameter is drawn, which means the angle in there would be 180 degrees. Well, we have 20, and we know whatever these two angles, they have to be the same because they're across from those congruent arcs. So when I take 180 and I subtract 20, I get 160 degrees. And I'm dividing that into 2 to get 80 degrees. So in here already, my 80 degrees is the portion that I'm looking at. So remember, I could start this off with 80 over 360 degrees. Because that's my portion is 80 out of the entire circle, which is 360. Now, I could set a proportion here if I choose to, right? And I would set it equal to the entire area of the circle underneath X. Or you could just multiply by the area of this circle. So again, remember our area formula is pi r squared. The radii in this case is going to be 6 because my diameter was 12. So essentially here I'm looking at 80 over 360 times 36 pi. And then since I'm leaving it in terms of pi, I could simplify this fraction if I choose to, right? But I know it's going to be times 36 pi. And I could just plug that into the calculator to make sure I feel good with that. But we end up with 8. And that should make sense here because if we look, 36 canceling out with that 360, we'd left over with a 10 on the bottom. So altogether, 8 pi is the area of this circle. So remember, I'm leaving it in terms of pi, so I shouldn't have any decimal in here. They didn't give me a unit to work with, so I could have units squared, but that's the general idea. Now, just to kind of remind us, again, all circles are going to be similar, no matter what circle you're looking at, because they all really have that same angle measure of 360 degrees. So because they're all similar, when I look at something like exercise 1 here, in the diagram below, we have 2 concentric circles with center O. That just means that they're 2 circles that have the same center, right? And they're like over, kind of looks like a bullseye. The radii are given, right? We have OC and OD for the smaller circle. OCE and ODF are drawn for the bigger circle. OC is equal to 4, while OE, the entire piece, is equal to 6. Which relationship between the length of the arc EF and the length of the arc CD is always true? Well, we've kind of talked about this question already, but really we should know that my arc lengths, we're talking about these pieces here, like CD and EF. So the comparison pieces are these two. They're always going to follow this similar proportion because they have the same central angle. So because they have the same central angle, they're still the same proportion of the entire circle. But they have different lengths because I clearly have a larger radii in the larger circle. So OCE is larger than OC. But the thing to keep in mind is we're talking similarity. It's not always going to be 2 units longer. And even in this case, it's not even 4 units longer. So there's no reason to pick choice 2. Just like there's no reason to pick choice 4 because in this case, it's never been 2 times the size, like 4 and 6. That's not 2 times the size. The only one that's going to make sense is choice 3 because all my circles, any circle I ever deal with, it's going to be similar to each other. Any kind of circle, any size, because all the shapes are going to match up with that 360-degree angle measure, but we're going to look more at finding the length of the arc of CD. So it's very similar to what we did yesterday. We have the 2 different ways to set this up. You can either set up a proportion. We could take the central angle over 360, and it's equal to the arc length over the circumference. So just instead of using the area, when I'm comparing it to the arc length, we're talking about the total distance around the circle. That's known as our circumference. So if I jump right in here to exercise number 2, a 90-degree sector is cut out of a circular disc with a radius of 4 inches. What is the remaining length of the arc? So we're looking for the arc length here. So again, we could do this one of 2 ways. To get my arc length, if a quarter of this circle was removed, right? A quarter of 360, we know that's 90. So the angle measure that I'm looking at in here would be 270. So remember, that's just because I'm subtracting out the 90 that we took away. We know it's out of 360 degrees. And now I can just multiply by what was the total circumference. So in here, be careful because they give me the radius of 4. So remember, my circumference formula is pi times diameter. So with that being said, if my radius is 4, my diameter is 8. And so essentially, since we took out 90-degree sector out of here, I'm left with 3/4 times 8 pi. And that's just going to leave us with 6 pi. This one should have said leave in terms of pi. It didn't. That's okay. But I do have a unit. This is in inches. Remember, because it's like a circumference, it's kind of closer to the idea of the perimeter. It's talking about the arc length around. That's going to be in our singular units, right? Like the area we know is always units squared, but our circumference is tied to the perimeter of a shape, so we just write it as inches. And like I said, it's just the same essential thing as what we did yesterday. So we just tie it into a real place where we could see this here. We have a garden has the shape of a circular sector such that its straight sides measure 50 feet in length and the central angle is 132 degrees. If the garden needs to be surrounded by fencing, how many feet of it are needed? Round to the nearest foot. So in here, it's basically asking us if the garden needs to be surrounded by fencing, how many feet of it are needed? Well, I have 50 and 50. That already gave me these 100, right, of this field. But we need to find my arc length. So we need to find how long this length is here. So, So as we look for that fencing all the way around, so same kind of concept, right? So we take the 132 over 360 because that's going to be the proportion of the arc length that I want. So remember, the circles are always similar, so they're going to be in that kind of proportion in here. Now, I just times it by what the circumference of the whole circle would be. So I know that 50 feet is my radius in here. So since 50 feet is my radii, that means 100 would have been my diameter, or 2 times the radius for pi. And in here, we want it to the nearest foot, so I'm just plugging it right in. You could simplify the fraction if you wanted to. You could play it around. But in here, I'm just going to take my 132 divided by 360 and multiply it by 100 pi. So yes, I'm going to include pi this time because it said to round to the nearest foot. So 150 115. Now be careful though. The 115 represents the arc here. So don't forget, if I want to enclose that whole fence, I got to add that other 100 feet from the two sides that we highlighted before. So altogether, I'm looking at 215 feet of fencing that would be needed to enclose this circular garden, this arc garden here. Now, what's the total area of this garden? So the same kind of concept. So this is just what we did in the previous lesson. I'm still taking 132 times 360. Now, because this is going to be the shaded inside portion that we're looking for, that area of the sector, I multiply it by pi r, my radius, which is 50 squared. And again, I'm just going to plug that right into the calculator. I'm going to let that do the work for me. 132 divided by 360 pi r, which was 50 squared. And we get 2,879.7932. So 2,880. But keep in mind, now this is feet squared because area is going to be terms of the square units. That multiplication's happening in there. And then for perimeter circumference, that is just the singular unit. Okay, so we could do it with both of those here. Just know the difference. It's the same setup, only we plug in area when it's for the area sector, and we plug in the circumference when it's for the arc length. Okay. Take a second and try exercise 4. It's the same idea. Now we're just finding the degree measure. So remember, in here, we said that you could do it either way. This one's, when you're finding the degree, it's probably a little bit nicer if you use that proportion method like we did yesterday. So you could do either method, but go ahead and just try to set up a proportion here. So pause the video, try this out, and then I'll give you a second, and then I'll come back and go through it with you. Okay, welcome back. So again, I was saying that it would probably be easier to set up a proportion. So we're looking for this angle measure in this case. So I like to call a missing angle theta. If you called it x, that's totally fine, but we automatically know that it's always out of 360 degrees. Now the difference here is they gave us that the arc length is 28 feet. So I know my arc length is 28 feet. That's the total amount we could go through. Now, when I set up this proportion, just like I did theta over the entire amount of degrees, 360, I'm doing the arc length over the total amount that the arc length could be. So I'm putting the total circumference in there, which is 16 pi feet. All right, because my radius is 8, so my circumference is 16 pi. So in here, I cross multiply 16 pi theta, and then I multiply 360 times 28 to get 10,080. And then I divide both sides by 16 pi. Remember to be careful here, because when the calculator reads this, it's just thinking that it's normal multiplication, PEMDAS in here. So make sure your 16 pi is in parentheses when you divide, or that you use your alpha y equals trick, because you want to make sure you get the proper degree here. We get 200.535. So to the nearest degree, 201 degrees. That's our central angle in there that the horse can travel. We have one last question to look at here. Now, this is just a regions question. The diagram below shows circle O with the radii AO and OB. The measure of the angle OAB is 120. The length of the radius is 6 inches. Which expression represents the length of the arc AB? So we're just going to set up our expression, 120 over 360 times the entire circumference would have been 12 pi. So now notice that's not an option. They give you the 6 pi to mess with you, but they simplify along the way here. So 120 out of 360 is 1/3. And now the only choice is 4, right? It's not going to be equal to 36 pi all of a sudden. We're not going to cancel out pi and play around with it, but choice 4. All right. Hopefully you're okay, feeling good about finding the area of a sector and finding the arc length of a circle, but we'll practice this more in class. Thanks for watching.